clear, if you follow the instructions step by step, you should be fine. Yeah, but we know a lot of details, we cannot put all the details in the project description, right? Yeah. So usually you can use this way. If some of the details I do not talk about, so you have some freedom to, use your own way to do it. Okay, just some reasonable, natural way to do it. Yeah, from my side, because if I do not put any requirement on it, so any way you do should be fine. Yeah, so that's the general principle. Yeah. All right, so here, based on the feedback from a few students, so let me talk about a few questions here. The first one, C.1, on data input and data validation. Yeah. So actually here, we do not have the data validation issue, yeah, but, some small problems. So I like to talk about a little bit. Yeah. All right. Data input. Yeah, so here, the detail part. So let's look at the data we need. Yeah, because we do polynomial evaluation. Okay, so let's look at. So here, to evaluate a polynomial, and our polynomial is in some general form. Okay, yeah. And we need to produce the data needed for this polynomial. Okay, yeah. So here the data. So let's look at what the data we need. First, coefficients of the polynomial. Coefficients. So that is the array, this array. Okay, yeah. All right. Second, the x value, right? Yeah. But some students also, talk about, because we ask our user to enter evaluation type, right? Yeah. Type of methods. Okay, yeah, type of methods. 0 exit. Method 1, method 2, method 3. Okay, yeah. So we can also include that part. All right, yeah. And this one, we generate, use a random generator or function. This x also by a random function. This one from keyboard, right? All right. So here, the question, all right. For A array, the range is in one, these integers, 100, from 1 through 100, positive integers. Yeah. All right. But we use our n 200,000 approximately. Yeah. So later I will explain this number. Yeah. So here, let's assume our polynomial degree is 200,000. Then one student asked me, because the coefficient value we can only choose from 100, but we have 200,000 plus 1 coefficient numbers we need to generate. Then we have a lot of repeated values, right? So here, no problem for repeated values. Repeated numbers in our coefficients. Yep. Actually, it's very common. When we write a polynomial, it's very common. Some of the coefficients can have the same value, right? It's quite common. And usually we do not require unique values for polynomial coefficients, right? Yeah. That's not a requirement. Yeah. So for the repeated values, numbers in coefficients, we do not need to worry about anything, right? Yeah. In our polynomial evaluation, we do additions, multiplications. We use repeated values. There is no problem. Okay, so we do not need to worry about that. Okay, yeah. So that's just but one student mentioned that, so I like to explain a little bit. Yeah. Other than that, after you generate coefficients, you put it aside, because you generate the coefficients before the user selects a method type. Okay, yeah. So when you start a program, you generate the data first before you ask a user to select from the method list 1, 2, 3. You generate the data first, because in that way, the generated data, actually, so here the data, all right, we mean coefficients plus x value. Okay, is used for all method selections. Yep. Because after that, yeah, so the situation is like this. When you run the program first, before you ask anything from your users, you generate the data first, the coefficients and the X value. You just store in your variables. Okay, yeah, ready for the remaining executions. Okay, then you print out a menu asking the user to select one of the three methods, right? So we expect the user select all three methods, 1, 2, 3, in any order. Okay, yeah. When they make several selections, you use the same data. Okay, and so here I mean same data for all selections. In that way, you can do comparison, right? In that way, your data keeps the same for all experiments. Then you expect to produce the same result. So we expect all those functions, all those methods to produce the same result. Right? Yeah. If you see, for example, when you run three methods, you generate three output numbers for the polynomial values. If you see some of them are different, then there must be an error. There must be an error. Oh, later there is a truncation error I need to talk about. Okay. Yeah, so let me delay, yeah, because here I already used almost all the space here. So there is a truncation error I need to talk about. Truncation error. Question, all right, yeah. All right, so the answer should be pretty much the same. Then, yeah, it's very likely, we cannot say 100%, but it's highly likely your answers are correct. Okay, yeah. And regarding the input validation, here you can see for the coefficients, you don't need to do validation, right? Because you generate the data in the range. That's valid, already valid. For X, X is in the interval between 0 and 1, right? Yeah. So we exclude 0 and 1, yeah, because that's too simple. Yeah. Exclude. Yeah, actually, in my description, I make a recommendation. So yeah, we do not need to use too many zeros here. Yeah. And the 0.99, for example, in this closed interval. Yeah. So you can generate. That means X value also valid. Yeah. Then the last thing, type of methods. Yeah, one student asked me, because you ask the user enter 0, 1, 2, 3, these four numbers are valid. They are valid numbers. But that student actually, that question actually pretty good. That question, student asked me, if a user enters a number out of those 4 numbers, number 5, number 10, or even a string, a character, things like that. Yeah. Then the remaining cases, the remaining cases, so not a valid number. Yeah. So you can handle by yourself. Not a valid number, you can output a message, right? Yeah, a message. Tell the user you need to select a number in, one of the 4 numbers. Just you have freedom. Okay, you can tell your user. Yeah. In my description, I didn't cover this point of detail. Yeah. So you just based on your natural understanding, so you make it complete. Okay. Yeah. So you give an option other than these 4 options. All remaining cases, you put in one special case, and you prompt output a message, tell your users you need to select one of the 4 numbers. Okay, yeah, things like that. Yeah, in that way, yeah, because that question from this student actually is a good one, because you need to consider all the possibilities from your users, right? In real world applications, you need to consider all the possibilities. Okay, yeah. So that is this one. So you need to, yeah. Although from my side, so I won't test you this point. Okay, yeah. For me, I only enter 0, 1, 2, 3. I do not check you, other, garbage input. Yeah. 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 But for you, so if you consider this point, that's good. If not, so no problem. Yeah. Because our main focus is at the algorithm side. Okay. Algorithm side. Yeah. All right. So here, just to let you know, the details, how much details we need to cover. Okay. All right. That's the first question. Second question on overflow problem. Now, one student asked me, if the implementation causes any overflow. Yeah. So here, actually, we won't have the overflow problem. Okay. Yeah. Because the data we considered, I put it under control. Yeah. I put it under control. That means no overflow could happen. Yeah. Yeah, because look at that. Our polynomial has this format. That end, yeah, because based on my experiment response time around 200,000. So if you make it a little larger or smaller, that's fine. And in our description, we make it fixed. Some students make it, make the user enter this number. That's okay. Yeah, that's okay. Yeah, but in order to make the requirement simpler, I make it fixed. Yeah, so you can, in your code, you can fix this number. Yeah. And around this one, the reason I want to control the response time for method one, yeah, if you make the degree number too big, then the response time could be very slow. You need to wait very long. If the number too small, then you may not see the big difference. Yeah. So you need to find an appropriate number that can give you, first, a big difference, second, not waiting too long. That's the reason I chose this number. And on my computer, this number approximately, takes 30 seconds, around 30 seconds. Yeah. And on your computer, you do not need that long, or sometimes could be longer than that. Yeah. So, but you can control this number if you like. Okay. All right. But here regarding the overflow, yeah, because the good thing to control the overflow, we need to control monomial. Yeah. If x value is too big, then when you do x to the kth power, then there is a possibility you can get an overflow. So here to avoid that, first I make x in this interval between 0 and 1. Second, our x is a double. Look at that, double precision. Double precision, its range is very big. Not integer, because integer, its range is not that big, right? Integer, integer, yeah, integer int, yeah, if I use Java, 4 bytes, right? If we use long integer, 8 bytes. Not very big integer. For double, although we use 8 bytes, but we can represent much larger number for double. Okay, yeah, much larger number. Yeah. So for that reason, yeah. So when our monomial, we can control between 0 and 1, right? Yeah. No matter how big is the exponent number, x to the kth, we always put x to the kth between 0 and 1. Then look at your polynomial, absolute value, okay? Less than or equal to the absolute value of all these coefficient numbers, controlled by this numbers, right? Yeah, this number, the largest is 100. Yeah, think about, less than or equal to 100 times n plus 1. Okay, yeah. The upper bound of this polynomial is controlled by this number, and that n we choose around this number. So you can see we control the value of this polynomial. So there is no overflow to be worried about. Okay, to be worried about. Yeah. But for that student who asked me this question, he sent me his code, probably some other problem. He just guessed. It could be an overflow problem. Yeah. All right. Then, from the previous slide, I mentioned that truncation error. Yeah, because this time no student asked me this question. Yeah. From last semester. Last semester, actually, many students asked me question related to this truncation error. So here, let me explain it. Yeah. So when you see this kind of phenomenon, so you will not get surprised. It's quite normal, okay? It's quite normal. So here, let me explain the truncation error. Very common in computation, truncation errors in, so here I'm talking about computer calculation. All right. So what's that? Yeah. Here, yeah. Let me use our project as an example. So we have three methods. Method 1, method 2, method 3. Yeah. Because you have, you know, result 1, right? You have result. Yeah. 2, you have result 3. Yeah. We expect them the same, right? Yeah. But after you produce these three numbers, when you compare, some of them may not be exactly the same. Yeah. All right. Because when you produce, usually the result, you have many digits, right? Yeah. So each one, you know, you have many digits. Yeah. So the problem is, it's quite normal. This portion the same. But the last a few digits, yeah, usually last a few, you know, last a few different. Yeah. The reason due to truncation error. Okay. Yeah. So you do not need to worry. You just treat them the same. Yeah. Yeah. Because, you know, this big block, you know, the most significant part, the same. The remaining, usually about 4 digits. You know, the last 4 digits could be different. Yeah, quite normal. Yeah. So why truncation error? Because in computer, you cannot represent a number accurately. Think about this. X to the kth. Yeah. When you calculate x to the kth, can you represent it accurately after kth power? Yeah. You have to truncate a few digits, right? Yep. Each term you have to truncate. The computer has to truncate some digits. And then you add up all these numbers, the digits truncated, the error part, added it up, it becomes bigger and bigger, right? And you use 3 different methods. That means the truncation style, the truncation ways are different. If you use different truncation ways, your output will be different. Okay, So for that reason, it's very normal that different truncation ways would cause the last a few digits with different values. Yeah, so that's quite normal. Okay, yeah. So don't worry about that part. You only need to make sure the first, actually the major part, the most significant digit part, and most number of digits, that part the same. Yeah. Yeah, it's quite normal. Okay. All right. Yeah. So that's this question. Yeah. Then another question I like to mention, yeah, so C.3 on repeated squaring implementation. Yeah. In the class, I give you the pseudocode, but actually that pseudocode mainly, I tell you the idea, right? The pseudocode, mainly I tell you the idea. So the problem is my pseudocode actually, some little things not covered in my pseudocode. Yeah, because one student used my pseudocode to implement, then got some problems. So you need to make it complete. Yeah. So here I give you, yeah. So later I test it. I make it a complete code like this. Yeah. Because the part I'm missing in my pseudocode, these base cases, you need to add these base cases. Yeah. Right. Yeah. Yeah. Okay. Yeah. So in my pseudocode, you know, because I mainly I cover the key part. Yeah. So the base cases I didn't include. Yeah. But when you write your real code, so you have to cover everything possible. Okay. Yeah. All right. So then the key part. So this is the key part. Okay. Yeah. And I tested. It works fine. Yeah. Okay. Yeah. So you just make sure, you know, your repeat squaring method implementation works correctly. Okay. Yeah. So here I just, you know, give you my version so you can take a reference. Okay. Yeah. All right. Yeah. So then, if you have any more questions, just let me know. Okay. Yeah. Hope you get this part, you know, quickly. Yeah, because we are very close to the deadline. All right. Yeah. So the project is not that too hard, but you still need to do a lot of work. Okay. All right. Yeah. So let me just finish my explanation of the project here, right here. Yeah. But I have, you know, I have half an hour. I have something left before, so I like to cover. Okay. Yeah. One thing from module 2, part E. Yeah. E.3, I gave a few questions, but I couldn't find time in module 2, part E. Yeah, so here, let me complete that part first. Yeah. Because this part, later you will see, yeah, and I will give you homework assignment number 1. In the homework assignment number 1, there are many questions related to this E.3. Yeah, so it's very important. Okay, so I like to first explain these these examples. Yeah. Show that n to the d. Yeah. This one we call a power function. Yeah. This is a power function. Yeah. Why we call it a power function? N is a variable. D is not variable. D is a constant. Okay, and this D constant, we just require here D greater or equal to 1. Yeah. Yeah. Actually, yeah. You know, any constant number greater or equal to 1. Yeah. Okay. Yeah. And the question asks you, the power function belongs to little o of that exponential function, a to the n. And this little o, it means the limit is 0. Okay? The power function n to the d over a to the n, this limit equals 0. That's the meaning of this little o. Okay? Yeah. So here you need to prove this limit equals 0. Okay? Yeah. All right. To prove that, yeah. So here we assume an integer, yeah. But later, because we here, yeah. So you know, here we assume the integer. That's for simplicity. Yeah. Because later, even if it's not integer, it is still correct. Okay. Yeah. It's not necessary an integer. Yeah. The reason in this example, to make our computation as easy as possible, we assume it's an integer. Okay. All right. Now we calculate this limit by the L'Hopital's rule. And you can see I change from n to x. Yeah. The original question we used m integers, right? Positive integers. Yeah. But here I change to x. Remember, we switch to continuous variable. When we use positive integers, that's discrete variables. For discrete variables, we cannot take derivatives. Okay? Yeah, no definition of derivatives for discrete variables. So for that reason, I switch to continuous variable first. And before we apply L'Hopital's rule, we can see it is infinity over infinity indeterminate form, right? Infinity over infinity indeterminate form. Yeah, because the numerator goes to infinity and denominator also goes to infinity. Then after that, we can apply L'Hopital's rule, and you can see the numerator, we use the derivative of power function. This is the formula, derivative formula of a power function, d times x to the d minus 1 power. Yeah, that's a formula. Yeah, so you can find it, okay, easily. Yeah, denominator also derivative of the exponential function. You can also find this formula. Okay, natural log of a, that's the constant part, multiply original power function, not power, exponential function, a to the x. Okay. After that, you can see it is still in infinity over infinity indeterminate form, right? Yeah. So you can apply L'Hopital's rule another time. Yeah. This time, taking derivatives, numerator, denominator, it becomes a little harder. Yeah. But you can still do that. Okay. All right. You can keep doing this if you have infinity over infinity indeterminate form. Okay, so you can apply L'Hopital's rule many, many times until you reach some point. It is not an infinity over infinity indeterminate form. Yeah, like this one, because x to the d minus d, yeah, after you do d times, we assume d is an integer, d times, then x to the 0, that's 1. Then the numerator is not an indeterminate form. The numerator is d factorial. It's a fixed number. When x changes, the numerator does not change. So it is a fixed number. Then you cannot apply L'Hopital's rule another time. That's illegal. Okay? Because it's not infinity over infinity. It's not indeterminate form. The numerator is determinate. Yeah, it's determined. Sorry, not determined. It's determined. Okay? Determinate. Yeah. So that means you have to stop applying L'Hopital's rule, but you can get the answer directly because the numerator is a fixed number, denominator goes to infinity. Denominator still goes to infinity. Then you can see a fixed number over infinity, that's 0. Yeah. So the answer is, yeah, after simplification, yeah, because you get that. So it's 0. Yeah. Then we proved that little o notation. Yeah. We can go back to, after we prove it for the continuous variable, then we switch back to the discrete variable based on the definition of limit. Yeah. So I mentioned that before. Limit, when x goes to infinity, that means you can take any approximation way to the infinity, right? Yeah. Any approximation way to the infinity, it's legal. Now we take consecutive positive integer way, that's also legal, right? Yeah. So we go back to our original form. We take n consecutive positive integers. Yeah. So that's legal. Yeah. So we get a conclusion. Yeah. All right. Okay. Yeah. Here. Yeah. Yeah. And in this question, so now after we prove it, then later we will use this. We will use this question. Okay. Yeah. So here, let me, yeah, because I mentioned homework assignment number 1, I will give you soon. Yeah. So we will use it. Okay. Yeah. When we use it, yeah, here we assume n to the d belongs to little o of a to the n, but when we use it, that d could be any positive d, is fine. Even non-integer is fine. Okay, yeah. But in my question, homework questions, I give you positive numbers. Okay, yeah. For simplicity. Yeah. All right. And D could be very large, right? It's a constant number. Can we make the constant number fixed very large, right? All right. Then let's look at the A. A, we only require greater than 1, right? We only require it is greater than 1. Other than that, no other requirement. Okay, all right. So based on this result, then I make my homework questions. Many students got confused or they couldn't get to the point. Yeah. So because I ask you compare which one is larger when n is very big. Yeah. One is n to the, I use, 1 million. Okay. 1 million, 60 after 1. All right. Another one, a to the nth. I use 1 point, yeah, because a, we only need, it is greater than 1. Can I put many 0, 1.01 to the nth? Right? So I ask you compare which is larger when n approaches infinity. Okay? Yep. If you answer this question by intuition, that could be wrong, right? Yeah. Because by intuition, most of you may feel, this number very close to 1. So then they just replace this number by 1. 1 to the nth, that's 1, or close to 1. How can you compare with this big expression, right? Yeah. But can you take a look at this result? We just prove it. That is correct. Mathematically, we proved it rigorously, right? It must be correct. Yeah. But that's different from the intuition of most of the students. That's something you will see in our homework assignment questions. Yeah. So here I emphasize this, big point. Yeah. All right. So let me complete remaining questions. Yeah. This time we compare log function and the power function. Can we treat this square root of n a power function? Because n to the 1/2. 1/2, although it's not an integer, it's positive, right? It's a positive, yeah. So we can treat it as n to the d with d greater than 0. So it is still a power function. But this time, we consider d a small number. Yeah, because we need to compare with log. We know when d is a large number, log function cannot compete with the power function. But how about when d is a small number? Can log function compete with power function with d a small positive number? Yeah. Here we answer that question. Okay, we still apply L'Hopital's rule. So we switch to continuous variable x. Yeah. And we take derivatives because we know it's an infinity over infinity indeterminate form. Yeah. So it's legal to apply L'Hopital's rule. After the derivative, the numerator reciprocal, yeah, but you need to multiply that natural log of 2. Yeah. Denominator, the power function derivative formula, we know d times x to the d minus 1. Okay, yeah. So here, this formula we take, just from there, but d with d equals 1/2. Okay, we take that formula. D times x to the d minus 1 power. Yeah. All right, we need to do simplification after that. Yeah. After simplification, we get this expression, but this fraction, it's not an indeterminate form. So do not apply L'Hopital's rule another time. The numerator is a fixed number. It's 2, fixed number. So denominator goes to infinity. So a fixed number over infinity, it's 0. If it is 0, then we go back to the original function with discrete variable n, positive numbers, integers, yeah, positive integers. So we get that little o expression, yeah, little o expression. Yeah. Then our conclusion. Now here I use square root of n, square root of n. Yeah, that's just a special case, right? Root of n. And we can have some general case, right? Yeah, yeah. Here, example, this one, this time we consider general case. Yeah. So this time, log part, we use natural log. We use natural log because the log base is not that important. Log base 2, log base 10, log base any integer number here, not much difference comparing with we use natural log. Natural log is most convenient when we take derivative. Yeah, natural log. All right. Yeah. So ln of n, natural log belongs to little of n to the d. This time, I only need a d greater than 0. That's good enough. Yeah. So you can imagine d could be a very small positive number. Yeah. Not an integer here. Yeah. Because when we compare with log function, we do not need a large power function. Yeah. We mainly we consider small power function. Okay. All right. L'Hopital's rule again. Still, we use the continuous variable version of the limit. Then L'Hopital's rule, it's infinity over infinity. Yeah. So I always check it. Okay. Infinity over infinity. Then you take a derivative. Natural log, its derivative is the simplest, just reciprocal function, 1 over x. Then denominator the power function. Yeah. So the standard derivative formula for the power function. After simplification, we get this expression. It's not an indeterminate form. The numerator is a fixed number. It's 1. Denominator goes to infinity when x approaches infinity. So the answer, it's 0. Now, here you can see we only need d is a positive number. This limit goes to infinity. No matter how small is that d. Okay? So then, all right, then now I have 10 minutes before I finish our class today. So let me talk about another case that's quite confusing. Yeah. Another possible question I may give you in our homework assignment number 1. Now, similar to this one, I already explained this case. Okay, compare a power function and an exponential function. The exponential, the base is very close to 1, 1.00, many zero after the decimal point, then 1. Compare that. Another similar question, yeah, based on this example. Yeah, it comes from this example. Okay, all right. Yeah, and that D, remember that positive D, that could be a very small number, but it's positive. It is close to 0, but it's not 0. Okay, then compare log base. Yeah, here I just use natural log. Yeah, okay, any base positive, base greater than 1. Yeah, but we require base greater than 1. Okay, yeah, natural log of n, and then power function n to the d. Can I choose a very small d? But it's positive. Okay, so here I choose 0.000. I put many zeros. 1. Okay, this power function expression. I ask you compare these two functions when n, approaches to infinity. Okay, yeah, so very, very large. Yeah, which one eventually is larger? Yeah, eventually is larger. Okay, yeah. If you answer this question by intuition, you may feel n to the 0 point, many 0, 1, the exponent number is very close to 0, right? Then you may feel n to the 0, that's close to 1, right? We know n to the 0, it is 1. Yeah. Some student answer the question by intuition, okay, then it's very likely they compare this function with this result. Yeah. Exponent number so close to 0, then it's very likely they replace the exponent number by 0, then this power function is, they feel close to 1. How can you use 1 to compete with natural log? We know natural log goes to infinity, right? But your power function, they feel close to 1. How can you compete with natural log, right? Yeah. But can you take a look at our example 2.7? In 2.7 tells us the log function cannot compete with the power function n to the d if d is positive. We don't mind how small is the d number, how close is the d number to 0. We don't care, but eventually n to the d, that power function will outgrow the log function. Okay, yeah. Although that it could take very long, a very big n number, but we allow n approaches to infinity, right? So we don't care how large is that n. When n approaches 0, eventually it will be there, right? Eventually n will pass that line. Okay, yeah. Then some students, they argue with me in this way, yeah, because they try to apply calculators, you know, even some online. Yeah, we know our hand calculator, little app on our cell phone may not be very powerful, right? It's quite limited. Yeah, our hand calculator, you know, any version, any kind, so its computing capability is quite limited. Yeah, but for calculation, for this question, we may need a lot more computing power, right? Yeah. So some students, they can find some online computing, you know, more powerful calculator online. So they try to do some experiments. Then, so because when you do experiments, that n to the 0.00001, that function increases very slow, very flat. Okay, the curve is very, very flat, you know. Yeah, because the reason is this: your n cannot be too big, right? Your n cannot be too big when you do calculation. Okay, it grows very, very slow, and your calculator cannot tell you its behavior when n is extremely huge. The calculator has the limit. It cannot tell you, you know, its behavior when n is extremely big. Okay, so based on your experiments in some online calculator, you may not get the correct answer. Okay, yeah. So some students use the online computing result, you know, to argue with me which one is larger. Because you can never use the sufficiently large n. Yeah, because the n you use relatively small. Yeah, but when we do math calculation, we can imagine super big n, right? N goes to infinity. Think about how big n is possible. Okay, yeah. And actually, I remember, in order to convince that student, I found that limit line, or that big n number, right? I found that expression. So I told that student, so that n equals, you know, for example, 10 to the, yeah, I found that n expression. Then I told them, if you use this big number, then the power function will beat the log function. Okay, yeah. So here, I use this chance. I give you the, you know, possible results derived from these two examples, 2.5 and 2.7. Yeah, you will have two similar questions. One similar to the, you know, first one, another from the second one. Okay, yeah, these two questions in our home assignment number 1. Okay, all right, so let me stop right here.